So happy spring, everybody. Today's topic is unconventional oil and gas, also known as fracking. And we have Bob Kleinberg from Schlumberger, expert in the area. He's co-author, primary author of the chapter you read, and co-author of the oil and gas chapter. And we're happy to have him come here and talk to us from the perspective of a fracker.
Thank you, Mike.
I was just going to try to turn up the...
Okay, right. Okay, good afternoon, everyone. I was thinking of coming in my Bermuda shorts and straw hat. So I understand this is a typical February in Boston. Lovely weather. Anyway, I have lived here 10 years, so I've been through those two awful winters, so I do know. But always a pleasure to be here at Harvard, and as I have in previous years, I'm talking about unconventional fossil fuels. This is sort of the second half of the lecture that you heard on Wednesday from Professor John Shaw when he talked about the conventional oil and gas, and I will be building on that to a certain extent. So first of all, just a word about the ground rules. I hope you have all read Chapter 17 in perusal. How many have read it? Very good. How many of you commented? Wow, you're either very studious or you're lying. Anybody just... Yeah, right. Anybody just page through and look at the pictures? Okay, so you all took it seriously. I will say that the comments this year were significantly more interesting than last year's. So I was pretty impressed. I will be responding to them. I didn't have a chance to do it since 2 a.m. this morning when I understand that the comments were closed, but I will be getting to that in the next week or so. This lecture overlaps with that chapter to a certain extent. It's, as you'll see, far from identical to it, however. Please feel free to ask questions as we go along. We will finish by 4 o'clock. I remember very well sitting in classes, watching the time go by after the appointed hour was over, and I have no intention of inflicting that on you. Anything I don't finish, you will have in the notes that Mike will give you. But we will finish by 4, and feel free to ask questions. So here's an outline of what we're going to be talking about today. First, just an overview of unconventional fossil fuels. What are they? What's the landscape? Then I've got sort of two major sort of technical sections. First about heavy oil, secondly about shale gas and tight oil. And we're going to go into more details in those two topics. As you'll see, it's a much broader subject, but I only have a little less than an hour and a half. And I've asked Mike to actually give me a whole course on unconventional fossil fuels. He has not done that, so we're just going to have to do the best with the time we have available. So first, let's get started with the normal petroleum system. You learned something about this on Wednesday. I think Professor Shaw did not use this particular diagram, which I rather like. I'm just going to go through it quickly, keeping in mind that you are already somewhat familiar with it. Basically, the story of oil and gas starts with source rock, which is this purple layer at the bottom. And that's basically fine-grained sediments, clays, very small-grained sand and limestone particles and so on, that are interbedded with organic matter. So this is basically dead algae for the most part. That gets compressed in the earth as more sediments are added on above it. And that's what's called source rock. Now, as those sediments are buried, they get deeper and deeper in the earth and therefore hotter. You learned about this 2 days ago. Oil and gas are generated, and they need to find a way up because they are less dense than the groundwater, which is pervasive in the earth. So they will tend to migrate upwards, and they're looking for migration paths, which are typically fractures as shown in this diagram. They will continue to migrate up in the normal petroleum system until they hit a trap, which is defined by the so-called seal rock or cap rock, shown in gray here. And then the oil and gas will accumulate underneath that seal in a buoyancy-driven fashion. So you'll have gas floating on oil, floating on water. It's like a bottle of salad dressing. They phase separate according to gravity. And so that's the normal petroleum system. Now, the unconventional fossil fuels, probably the most general definition is that they do not follow this scheme. Other things happen, and you'll see that depending on the fuel we're talking about, different things happen. So this is sort of an overview of the unconventional fossil fuel, conventional and unconventional fossil fuel landscape. I'm not going to go through every box. It'll be in your packet of slides for your reference. But basically, on top are the conventional oil up here, which includes crude oil, natural gas liquids, and then the unconventional down here. And there's a lot of different kinds. We're only going to be talking about these first two boxes, the so-called heavy oil, and then the so-called light tight oil. Again, just for your reference.
Could I just add?
Sure.
We're going to be discussing coal to liquids and gas to liquids in next week or the week after.
Right. Not my problem. Okay, so there is quite a lot of this stuff in the earth. This is a chart that came out in 2013 from the International Energy Agency. On the horizontal axis is technically recoverable oil reserves in trillions of barrels. On the vertical axis is the price, full cycle break-even point, rather technical, we can talk about that if you wish, in dollars per barrel. And this light green band is oil that's already been produced. We have used about 1.2 trillion barrels of oil, and it's a sphere something like 7 kilometers in diameter, huge amount of oil. But there's still quite a bit more left. In Middle East and North Africa, conventional oil is about another trillion sitting there, mostly in Saudi Arabia, Iran, and Iraq, and surrounding countries. Other conventional oil elsewhere in the world. As you see, the Middle East, North Africa has the cheapest oil available. Others sort of range from $10 a barrel up to $70 a barrel. The extra heavy oil we're going to be talking about today is up here, just barely profitable at the present price of crude oil, which is about $55 a barrel this month. And then this LTO is the so-called light tight oil, which I'm also going to talk about today. The width of that bar is very much underestimated, partly because this chart is 4 years old, but to this day it's not really known the dimension of that resource, but it's considerably larger than indicated on this chart. So the overall story is that we are not going to run out of oil. We will have to stop burning it before we run out, that's for sure. So let's move on to the first special topic, which is heavy oil. I'm going to be talking about petroleum geology and geochemistry, production technology, environmental issues, which are very important, and I'm going to end up this section by talking about pipelines versus crude by railroad, which I think is kind of an interesting topic these days. So let's just look at some petroleum geology. This is basically sort of horizontally is sort of distance east to west. This is actually, although it doesn't say it, this is actually sort of a model of what goes on in Alberta up in Canada, Western Canada, where you have this source rock laid down. That's the fine-grained minerals plus organic matter in these sort of orange and red bands. And then what happened is that the Rocky Mountains grew up pushing down those organic-rich layers and thereby creating conventional oil. I mean, just the same old oil that we like to pump out of the ground and into our gas tanks eventually. And some of that is trapped in Alberta, and Alberta has some conventional oil deposits shown schematically here. However, a great deal more of the oil found its way up. Now, unfortunately, in Alberta, it did not find a seal. It did not find a cap rock. So it kept moving toward the surface until it reached sediments that were less than 80 degrees centigrade. Now, what's the significance of 80 degrees? That's basically the point at which bacteria are killed. So there's no microbial activity higher than 80 degrees centigrade. So this oil down here, which has been sitting there for millions of years, is preserved from bacterial degradation, whereas anything that gets up too close to the surface, I'm talking about a few hundred meters, basically a kilometer or so, basically starts being attacked by microbes, and it's also oxidized by rainwater, which can penetrate, again, the 100 meters or so, a few hundred meters into the earth. So that changes this light oil, which John Shaw described last time, these short chain paraffins, the small ring compounds, that whole panoply of things that we find in conventional oil. It changes it into something very much uglier, very viscous, and essentially self-sealing. Once you start accumulating this bad stuff, that's what's left over when the microbes are finished, it seals itself in, doesn't require a cap rock near the surface of the earth. And what do those ugly molecules look like? So here we are. This is typical molecular structure of heavy oil. It is kind of one big molecule, if you will. Everything's connected up here. It has aliphatic carbons. It has naphthenic, which are those rings without double bonds. And then it has aromatic cores. So this stuff, for those of you who have taken chemistry and have some intuition about how molecular structure correlates with viscosity, for the physical chemists in the room, this thing is going to be very viscous. And therefore, first of all, hard to get out of the ground. And then when you get to the refinery, it's going to be hard to refine. So it has less value than conventional oil. So why are we worrying about it if it has less value than conventional oil? Well, the answer is there is a great deal of it. Now, this chart basically has sort of two property axes. The horizontal axis is a density axis, and there's this peculiar unit called API gravity. It's defined in the chapter 17. You can look it up if you don't recall. Running from 0 to 50. It's basically an inverse density scale where API 10 corresponds to 1 gram per cubic centimeter, same as water. And then the low density is on this side, the high API gravity, so to speak, and the high density is on this side with the low API numbers. Now, more or less arbitrarily, but this is generally agreed upon in the industry, the cutoff between light oil and heavy oil, heavy being the higher density stuff over here, is 0.922 grams per cubic centimeter. So everything on this side is sort of considered conventional, and that has viscosities generally less than 100 centipoise, which is like olive oil. Okay, you're familiar with that. Everything on this side is heavy and has viscosities ranging from maple syrup, ketchup, peanut butter, all the way up to road tar, 1 million centipoise. And in fact, Canada, up in Alberta, has an immense amount of that stuff. Now, the size of the bubble corresponds to the volume of the resource. You can see this California heavy oil over here. Looks like maybe a little satellite orbiting Uranus. 1 billion barrels have been taken out of California heavy oil in the last century. So these bubbles represent a great deal of oil if that little tiny satellite there is 1 billion barrels. So huge resource if you can get it and use it. So how do we get it? Well, there is a myriad of methods, and I'm sure you would want me to go through every single one of these boxes, but I'm sorry, I'm not going to do it. There are numerous methods that have been devised by petroleum engineers over the years to get heavy oil out of the ground. I'm going to describe 2 of them. The first one I'm going to talk about is open pit mining. This is really basic. So I said these occur near the surface. You get out your steam shovel, toss the stuff into a truck, drive off, and separate the sand from this tar, which is really what it is, tar, the 1 million centipoise stuff. It's used in Canada for very shallow sands. Very high recovery factors, steam shovel gets it all, absolutely. High environmental impact. What do I mean by high environmental impact? Well, here is a aerial photograph of the Athabasca tar sand mining region in sort of north central Alberta. This was, as you see, taken in July 2009. These massive sort of disturbed areas have not gotten any smaller. You can see where the steam shovels have been working. It's pretty obvious. So, you know, I actually took out the slide which actually showed the worst of it, but it kind of leaves a big environmental mess. You get these big pits. And these are, you know, on the order of 10 kilometers, you know, in size. So they're pretty substantial, and there's several of these. Now, the government of Canada, you know, our northern neighbors are very progressive and environmentally conscious. So they have mandated that these giant disturbed areas be reclaimed and restored to more or less their original state. How have they done? Answer, not very well, not very impressive actually. So this is sort of data from 2009 to 2013. Cumulative area disturbed is on the vertical axis, and the gray, sort of the whole bar is disturbed. The green bar is reclaimed according to Canadian law. Now, Mike looked at this, and his comment was, they haven't been doing a very good job, have they? And in fact, you'll notice the data stops at 2013. It's not because I was lazy. I've been going back every year and looking for this data since 2013. They haven't published it, and now this year, the link died. So I think this is what governments do when they don't really want to talk too much about their programs. They just stop collecting or at least publishing the data. So anyway, boo for Canada. They could be doing better. However, I will say that, and just to put it in perspective, the total disturbed area is something less than 1,000 square kilometers. That's kind of equivalent to the area inside the 495 road around Boston, roughly speaking. It compares with 660,000 square kilometers in the province of Alberta. So you know, you really ask yourself, okay, we are going to truly mess up, I mean badly mess up, 1,000 square kilometers to produce a world-class source of energy. Is it worth it? I mean, I think this is something that the people of Alberta and the people of Canada have to decide for themselves. To me, the answer is, you know, not entirely obvious. I mean, you know, it's a bad degradation, but in an area that is small compared to the size of the province it's coming from.
Quick question, sorry.
Sure.
About that graph, is the disturbed area, is that the land that's been disturbed and sort of finished with, or is that still sort of the area that's under active production?
Well, both.
Okay.
Some under active production, some done. Yeah. Okay, let's go on to the second method that I'm going to talk about, which is in this broad method of steam methods. And steam is very popular for heavy oil, and I'll show you why in a minute. And what I'm going to talk about in particular is this special method called steam-assisted gravity drainage. It's abbreviated SAGD, used in Canada and more elsewhere. Again, high recovery factor, production from shallow sands with weak cap rock. So it's versatile, and here's what it does and why it works. So this is a graph of oil viscosity. Horizontal axis is temperature in degrees Fahrenheit on the bottom scale, and I put a centigrade scale on the top for the scientists here. So here's 10 degrees centigrade, 200 degrees centigrade. The vertical scale is viscosity again, but this is not even on a logarithm scale. It's kind of logarithm of logarithm. As you see, the orders of magnitude are getting closer together as we go up. But on this peculiar kind of plot, the viscosities sort of plot linear against temperature. And each colored line is basically a different oil-bearing province. Most of them are in Canada. Lloydminster is actually in Saskatchewan. Kern River is California. Cold Lake in Alberta. Midway Sunset, California, and so on. And these are all, these three at least are Alberta. So basically, if you've got road tar and you need to get the viscosity down to, say, 10 centipoise or so in order to pump it, in order for the stuff to drain into a well and pump out, raise the temperature to 200 degrees centigrade. How do you do it? This is an increasingly popular method, SAGD, steam-assisted gravity drainage. What you do is that you drill 2 horizontal wells parallel to each other, 5 meters apart, and these wells are typically hundreds of meters long. So this is a real interesting engineering challenge. I'm going to tell you later how to drill a horizontal well, so you'll be able to do it yourself. But this is now a, I would say, technically sophisticated but now routine task of drilling 2 horizontal wells 5 meters apart. In one, you pump in steam. It heats up the rock underground that has all that road tar in it. It softens up the road tar until it's about like maple syrup or olive oil, which then drains down into the lower well where it's pumped out back to the surface, and there you go. And so this is very effective and has a high recovery. Now, you might ask yourself, okay, steam, where does the energy come from to make the steam? I mean, you've got the Athabasca River, which supplies the water. Well, you burn natural gas. So you're thinking, hold on, you were burning natural gas to produce oil. Does this make sense? And it does make sense if those of you who have done the problems at the end of chapter 17 have gone through the math. At least a few of you are nodding. Some are smiling, some are nodding. Okay, that's good. You'll see that it makes sense both on an energy return basis and a financial return basis to burn natural gas to produce oil. So, okay, that all works. There's going to be a new question which you will not have available to you about the carbon effects of that. But I'm going to talk about that right now anyway. So let's just look at the greenhouse gas impact of this sort of operation. So this is from an IHS report, came out a while ago. The numbers haven't changed though. And these are for all different kinds of oils. Now at the top there's West Texas Intermediate, which is sort of classic conventional oil, low viscosity, easy to pump out of the ground, no steam involved. So that's up here. And then at the bottom is these Canadian tar sands and so on. And then there's all different kinds of things in between, oils from overseas and so on, produced by various methods. Now you'll notice that the red bar is the same for all of them, and that is the greenhouse gas impact of just burning fuel in your gas tank. So you guys, the consumers, are responsible for most of the greenhouse gas impact of fossil fuels. And you should keep that in mind. It comes to 400 kilograms of carbon dioxide per barrel of refined product. Now, the sort of yellow and white bar is kind of our side of the question. That's the greenhouse gas impact of extraction, which is what I just talked about, refining, and transport. So if you have a kind of oil that requires burning natural gas to get out of the ground, it's going to have a high greenhouse gas impact. And of course, there's been quite a lot of public debate about whether we should be using this kind of oil at all, the kind that's in Alberta, the heavy oil, that has the higher greenhouse gas impact, as shown here. Oil sands low, oil sands high, market average for oil sands. So it's sort of at this end of the spectrum. Just need to point out that the greenhouse gas impact of the worst oil sand is about 26% greater than the greenhouse gas impact of the easiest, lowest quality oil. So the difference, you shouldn't think that these oil sands are hugely different than what you're burning anyway, because let's face it, it's mostly you and your automobiles. But that said, let's just look at what the value to society of that greenhouse gas impact is. So what I've done is I've assumed a $40 per metric ton social cost of carbon, which is sort of a round the world kind of average that people are now settling on. It changes with time, and it's kind of a slippery number, but it's what most people are using these days. At $40 a ton, basically the social cost of acquiring and burning West Texas Intermediate standard crude oil is about $19 a barrel. The worst heavy oil up in Canada, $23 a barrel. So that's really the difference in sort of social impact quantitated and put with a dollar sign. And I'm not saying it's insignificant, but that's just what it is. You can judge for yourself. Now, price of oil these days is about $55 a barrel, as I mentioned. So if you actually imposed, say, a carbon tax of $40 a ton, you'd be increasing the price of gasoline by about 50%, which is like taking it back to where it was a couple of years ago. Of course, people would scream. That's kind of really not very acceptable to do that by government fiat. But I just want you to consider something. If you introduce this tax slowly over 10 or 20 years, do you think anybody would notice? I don't think so. So, we can do something about these problems if there is a will, and it doesn't need to bankrupt anybody. Yes?
Do you think that if the price increased, would it make that big of a difference? Like you said, that was what it was a couple of years ago, right? So it seems like in adding the cost doesn't seem to change much.
Yeah, that's also true. Yeah. So, in fact, there's a big debate about carbon taxes. Are they really effective? And I think you're arguing that they're not necessarily effective. This is the so-called social cost, so it's a fair cost by some measure, but I think that's a very good observation. Let's talk about transporting this oil out of Canada. So this is a map of the existing and proposed pipelines for taking away this Western Canadian oil, most of which is this heavy oil stuff. And you've all heard about the Keystone XL pipeline, which is this dotted blue line, dotted because it doesn't exist yet. You see there it crosses the Canadian border. That's the big hang-up, as you know from the news. So what is the real impact of the Keystone XL pipeline? Well, let's look at some economics first. I started this slide with a comment that President Obama made back in November of 2015. He said, this is a quote, "This pipeline would neither be a silver bullet for the economy, as was promised by some, nor the express lane to climate disaster proclaimed by others." Honestly, as a professional in this field, this is just dead on. I think he's absolutely right. But let's just look at some numbers now, and we can decide for ourselves. So here's just some facts about Keystone. It runs from Hardisty, Alberta to Steel City, Nebraska, 1,900 kilometers. Capacity 830,000 barrels a day in a 36-inch diameter pipeline. That's about a third of the total oil production, heavy oil production in Alberta. So it's really a substantial part. It can also be handled by 10 trains, 10 railroad trains, each of 100 cars, 100 tank cars, traveling south. Now, you might remember from chapter 16, we had this graph, which, believe me, we spent a lot of time and effort on, showing the cost of various transportation modalities for oil, gas, and coal. And if you study that graph carefully, you'll see that the difference between the rail and pipe is $7.65 a barrel. In other words, if you send it by railroad, it costs $7.65 more than if you send it by pipeline. So this is why people are so eager to build pipelines, because you save a lot of money, basically, in transportation. Now, a year ago, when I gave this talk last year, this was really an important distinction. Why? Because back then, last year, West Texas Intermediate, our standard North American conventional oil, was selling at Cushing, Oklahoma at $29.42 a barrel, whereas the Western Canadian Select, which is the heavy oil out of Alberta, priced at Hardisty, Alberta, was $15.12 a barrel. Now, why such a huge difference in the value of those barrels? Two reasons. First of all, the heavy oil is a lower grade oil that requires a lot more refining. That's part of it. And the second reason is transportation cost. Cushing, Oklahoma, right in the middle of the American oil and refining complex, or nearby it. So transportation minimal. Hardisty, way up there in Alberta, with pipeline constrained and railroads. Yeah.
So is the heavy oil actually getting pumped through that pipeline, or is it getting refined first and then pumped?
Okay, here's what happens. The heavy oil is too viscous to pump. But there's not, the Canadians don't have the refineries to process this oil. It's got to be processed on the Gulf Coast down in Louisiana, Texas. So what they do is they use what's called diluent, which is a light oil, sort of low molecular weight, which is piped up to Canada in a different pipeline, mixed in up there, and then both are piped down together and separated at the refinery, and then the light stuff is then sent back up. For more, yeah, I know it's complicated, but really, honestly, people make money doing this. So, okay, it works. So that's how they get it to pump it. Yeah. Okay. Very good question. Now, back, it costs a lot to produce this oil, about $20 a barrel at the minimum, and therefore. Last year, the Canadians were losing $5 on every barrel they produced. So it was uneconomic. So whereas if the pipeline had been there, this price would have been $7.65 higher, and they would have made $1 or $2 on a barrel. Big difference between making $1 and losing $5. So a year ago, the absence of that pipeline made a big material economic difference in the viability of those tar sands. Okay, today, price of Western Canadian Select is now $40 a barrel, so they make money either way. Obviously, they would love to have the pipeline because then they make $7.65 more. So that's the economic side. However, times have changed. So here is the, so I showed you the map. Now here's the numbers that go with the map. Horizontal axis is years from 2013 to 2025, so there's some projection involved here. Again, this is from IHS, which is a very good estimator of future trends, I would say. Vertical axis, thousands of barrels per day, so you're talking millions of barrels. And the red line is basically what Western Canada wants to export to the United States, and or at least out of Alberta. Now, Keystone is the old pipeline that has been there. Keystone XL is the new one. Now, they thought that was going to come online years ago, because it's been held up by American politics, et cetera. You all know about that. In the meantime, two other pipelines have snuck in underneath them, kind of sort of with the environmentalists being somewhat unaware. One is this Clipper Line 3, which is just coming on the next year or so. Another is this Trans Mountain expansion. One crosses the US boundary, the other goes to the Pacific coast. And you see that now that you've added in these two pipelines, which have kind of been sneakily snuck into the system, Keystone XL is kind of irrelevant. And TransCanada, which is the developer of that pipeline, has applied, Trump administration has applied for a permit to go across the border, but I question whether they'll actually build the pipeline at this point. I mean, it looks uneconomic. So. On the other hand, let's look at the other contentious pipeline, Dakota Access. It's also been in the news lately. This doesn't cross the border. It goes under this river in the Indian reservation. And in that case, it is highly relevant because without the Dakota Access, basically a lot of the oil coming out of North Dakota, is going to have to go by rail. So that is still, I would say, an open issue. Now let's have a closer look. Yeah.
Sorry, one more question. When you load up the oil in rail cars, do you have to add light oil to that as well, since it's so viscous? Or?
No, the heavy oil, I think they just kind of pour it in, I think. At least probably the million centipoise probably has to be somewhat diluted because that's kind of road tarry, but probably anything up to ketchup is okay to fill up. Now, the oil coming out of North Dakota is very different because that's a very light oil with a lot of very volatile ends, and that actually provides a significant hazard to rail traffic, as you will see in a moment. I think you know what's coming. Yes?
This might be too far-fetched or hard to answer, but is there any chance that there's some kind of innovation in terms of breaking down these heavy oils, like catalytically, early on, like say in Canada, in these remote places, to the point where this investment in the pipeline ends up being more like putting the companies into the red? Is that a possibility at all? Or like you're pretty confident that we wouldn't come up with that innovation and that this pipeline would still be relevant?
Well, the pipelines are always relevant because whether it's refined product or crude product, it's got to get from the place where it's abundant to the place where the consumers are abundant. That's on our side of the board. So that doesn't change the pipeline issue. The question of whether we can do a better job of refining and somehow magically breaking down the heavy oil to more usable stuff without having to go to these specialized refineries on the Gulf Coast, that's a great chemical engineering question. And yeah, like better catalysts, I mean, you know, that's a field that's been progressing for the last 150 years. And yes, one can see more improvements. Whether it'll ever be economic in Canada, I don't know.
Thank you.
Yeah. Okay. So let's take a closer look at this crude by rail issue, since that's really what's competing with this Dakota Access situation. So I've got a map here of crude by rail routes. So the darker, the redder the colors, the more traffic. So this is 25, what the heck is it? 25 trains per day or something like that. Weekly average of crude trains. So this is more than 25 a week, I'm sorry. So North Dakota is sort of the epicenter for all this new production that's coming out by train now. A lot of it's going to Albany, New York, a significant amount going up into the Seattle area, presumably for export, and then stuff going down to the Gulf Coast for refining. So that's where the trains are going. Now, I think you all know that pipelines are actually pretty safe. They have a relatively low accident rate, although not zero. I mean, there are pipeline leaks where you hear about leaks of hundreds or thousands of barrels. A barrel is 42 gallons. So bad, not catastrophic, but bad. But then with railroads, the risks are really significantly greater. This, you know, you need to go to the web and you find hundreds of such photos. This one happens to be CSX near Lynchburg, Virginia. You know, if I were there, I would advise these firemen not to stand there. That's actually a stupid place to stand because these things can blow up and have blown up in various places. So this is one thing that happens. It's, you know, obviously you want to minimize it, but it does happen. Another point of view, and this is something I just learned just in January, just last month when I went to an economics conference. This is work out of Carnegie Mellon University, where the researchers looked at the social cost of pipeline versus rail transport. Now, they've taken out the accident factor because they assume that the carriers are going to pay for the accidents. So this is just everything working normally with no accidents. And it's basically broken down by pollutants. Now, they've been pretty careful. They've looked at the air pollution problems associated with pipelines, which is like compressors and pumps and so on that you need to run pipelines. And they've also looked at pollution from railroads, which is mostly diesel locomotives. And the numbers are pretty startling. So just looking at nitrogen oxides, social cost for a pipeline, and this is in dollars per million barrel miles, okay, dollars per million barrel miles, $28.15 for a pipeline, $2,500 and $2,500 for the railroad, and so on. Here's CO2. Again, I think this is a $40 per ton number. Railroads are somewhat worse than pipelines, so not a huge difference. But there's huge difference in things like particulate matter, which of course diesel engines do emit particulate matter. Compressor stations on pipelines don't. So when we're evaluating kind of the environmental issues of not building pipelines, you really need to look at all factors. And I think this paper has really added to that debate in a very constructive and interesting way. So, okay, that's it for heavy oil and pipelines. Yes?
So in this country, does the railroad system and the pipeline belong to the same company or different companies?
Different companies.
So are they competitor or collaborator?
They're competitors.
So which means if I were the railway company, I will be really unhappy with the pipeline construction because they are taking my business away.
Yeah, that's right. And the railroads have built a lot of tank cars in the last 5 years. I mean, they have been on a tank car binge. Let me go back just to illustrate that. Okay, so the blue, which I didn't really talk about much, is the rail loading capacity. Every one of those steps represents a lot of tank cars being built by the railroad companies. And the specifications for those tank cars have been improving because they want to make them more accident-proof. So those tank cars are becoming more expensive. So you are absolutely right. There's winners and losers in this debate.
So if I were the railway company, I will abandon those pipeline crossing my railroad.
You need to talk to the Federal Energy Regulatory Commission. They probably do read amicus briefs along those lines. Yeah, okay. I'm just dealing with the technical level here. Yeah.
So I was wondering, if you don't build the pipeline to Canada, does that mean that you guys would import oil from some other place?
Well, that's a really good question, because you're raising the price of Canadian oil by $7.65. So there's competitors for that refinery capacity. Mexico has the Mayan crude. Venezuela sells us heavy oil, plus country elsewhere. But really, it's Canada, Mexico, and Venezuela that are big three importers into the Gulf. So yeah, so they probably don't want. You see, those competitors don't want to see pipelines. But you know, Venezuela is in big trouble. Their industry is collapsing, so they've got a problem. Mexico is actually doing better. So the Mexicans are probably secretly hoping that we don't build any more pipelines. Yeah, maybe not so secretly. Okay, on to the next topic. So shale gas and tight oil. This has been in the news a lot. You've heard about fracking, as Mike mentioned. And so this is kind of all about fracking, although this part of the talk is going to go well beyond that. We're going to talk about reservoir properties, horizontal drilling. I'm going to tell you how to drill a horizontal well. I'm going to tell you how to frack wells. I'm going to talk about frack fluids, which is always a favorite topic here in the School of Engineering and Applied Science. A bit about economics, and then if we don't run out of time, I'm going to talk about the rest of the world. So back to the normal petroleum system. Now, remember that the heavy oil was the stuff that just escaped toward the surface until it got self-trapped. So the gas shale and tight oil story is quite a bit different. So that's basically hydrocarbons which never got out of the source rock or never got very far away from the source rock. It's the opposite problem. They were trapped sort of deep and did not make it into these reservoirs which are buoyancy driven and gravity segregated and all that other good stuff. They're still mixed up with this very fine sediments, buried very deeply, very low porosity, all kinds of bad properties if you regard it as an oil reservoir. Whereas these rocks have great properties for oil reservoirs. So let's look at that in more detail. So the title of this slide is Pore size controls how fast oil or gas will flow to the well. Now, this part of Chapter 17 really got the most comments of any, which surprised me. And people want to know all about gas flow in these particular situations and oil flow. I just want to mention now, I'm just going to offer, I could like throw papers at you, but really it's important to see the whole context of this problem. And for anybody who is interested in flow of hydrocarbons through porous media, please come and see me afterwards, and we can set up sort of a little seminar. I have a pre-made talk that I've given at MIT. MIT is that tech school at the other end of Massachusetts Avenue. So it might be worth your while. If you're really interested, you really want to get the whole story, and so I'm going to offer that as a sort of separate module. So come and see me. And really as many can come as you like. I've got this nice 1-hour talk that really explains it in context. But for now, we're going to do the quick flyby and just look at the big picture. So here's the big picture. So on the left is a photomicrograph of reservoir rock. This is, I would guess, my guess is this is from the North Sea where you have rocks like this. These big boulders are sand grains, quartz. Here's a scale bar, 50 microns. And then here's a pore. It's about 50 microns in size. This is like excellent conventional oil reservoir rock. Now, how big is 50 microns? Well, 50 microns is about the diameter of a human hair. So what I'm telling you is that the best reservoirs in the world, the oil flows through channels the diameter of a hair. And in fact, if you took this rock and it was filled with oil would slowly drip out of it as you held it. I've had that experience. Now, so that's really great. Now, what about this gas shale? So this is one of these new unconventional resources. Well, here's another photomicrograph, and here's another quartz grain over here and over here. And this is pore space. But now, the pore space is not open, as it is in the conventional reservoir rock, but it's choked with organic matter. Remember, these rocks have been co-deposited with organic matter, which is squishy, compressed dead algae, which fills up the pores. Now, the organic matter itself is porous, but the pores, but look at what size they are. This is not a 50 micron scale bar, it's a 500 nanometer scale bar. So the scale bar is a factor of 100, and these little pores are about 1/10 of that. So the pores are about 50 nanometers, not 50 microns. That's a factor of 1,000 difference in pore size. And that tells the petroleum engineer all he needs to know about the productive capacity of these rocks. Okay, how does he know? So to know, you need to go do some physics, and we look at Darcy's law, which is sort of like Ohm's law. There is a volume flow term, Q, which is dimensions are cubic centimeters per second, cubic centimeters of fluid per second. There's an area term, and then this K over mu is sort of like conductivity. K is permeability to fluid flow in meters squared, if you will. Mu is viscosity, and then this grad P is the pressure gradient, and that's sort of like the voltage in Ohm's law. So here's sort of the definitions up here. In practical units, people talk about Darcy's, which is an oil industry unit, which is about 10 to the minus 12 meters squared. So as I said, the rate of flow is proportional to the square of the pore size. We are down 1,000 in pore size, which means the rate of flow is down by a factor of 1,000,000. So what are these? So let's look at some numbers. So water filter, 10 Darcy's. Good oil reservoir, 1/10 of a Darcy. Good gas reservoir, 10 to the minus 3. And this gas shale, 10 to the minus 7. Oh my God, it's like 1,000,000 times worse than this good oil reservoir. However, we're dealing with gas, not oil. So we have to look at viscosity, which is in the denominator over here. And crude oil has a viscosity of 1 centipoise at reservoir conditions. That's a good crude oil. Natural gas, about 1/100th of a centipoise at reservoir conditions. So at least you get a factor of 100 back. But when you put it all together, you've got a big problem, as you'll see in a minute. The other factor that comes in, this A, is contact area. And in a vertical 20-centimeter borehole, typical, in a 30-meter thick reservoir, typical, you have about 20 square meters of contact area. So if you put together some of these numbers, you wind up with a decent well. And let's look at how that works on the next slide. So good conventional oil reservoir, 10 to the minus 1 Darcy, 1 centipoise, surface area, 20 square meters, great well. Look at the gas reservoir. The permeability can be 100 times smaller because the viscosity is 100 times smaller, K over mu. And with the same surface area, the same well technology, you get a good gas well. In order for shale gas to work, the permeability 1,000,000 times smaller because the pore size is 1,000 times smaller. You're dealing with the gas viscosity, so you need a factor of 10,000 more, which is 200,000 square meters. 200,000 square meters. What is that? Well, it's kind of like 2 Prudential towers, each of which is about 100,000 square meters of floor space. So you think, oh my God, this reservoir is, okay, 30 meters thick. I could drill a borehole of any reasonable size. How do I get all that surface area? How can I possibly get all that surface area? And there's really only one way to do it. And that is to not just drill through the 30 meters and use that 30 meters to provide the surface area, but to go down to that productive formation and drill horizontally for 1, 2, 3 kilometers. You keep the well bore in the productive formation for not 30 meters, but for 3 kilometers. And then you have to start fracturing because you still don't have enough surface area. So here I've done a simple sort of calculation where these formations, productive formations, are typically 1.5 to 4 kilometers deep. So you drill down 1.5 to 4 kilometers. You have a horizontal run of 1 to 3 kilometers. You put in 40 fractures, each of which has a diameter of 200 meters, a fracture height of 30 meters, that's the size of your productive formation, giving you a surface area of 500,000 square meters. That's more than we need, but it has to be more because these wells cost a lot more to construct than just the straight down vertical. So they have to be more productive, and in fact, you can make them more productive. So that's kind of the secret for these tight oil and shale gas formations. You need to have the horizontal drilling, and you need to have the massive hydraulic fracturing. In this case, I've specified 40 fractures along that horizontal run. Fracture, 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 fracture. I only show 3 here. So that's what you have to do to get gas or oil out of these very, very low permeability formations. Now, horizontal drilling, how does that work? Because, you know, if you take your Black & Decker at home and a piece of wood and drill down, and then you want to go horizontal, you will break the drill bit almost instantly. So are you wondering how it's possible? Everyone's wondering. Okay, fine. Good. So the secret is that you are drilling kilometers. So if you take a piece of 4-inch diameter pipe, which has a wall thickness of about 1/3 of an inch, and rest it on a pipe stand, it will sag. And in fact, it will sag about 10 degrees per 100 foot. So that determines the maximum radius of curvature, essentially, the minimum radius of curvature, I should say. So you can turn about 10 degrees per 100 feet, just because the pipe, that 4-inch pipe, has that much flexibility. Now, to do that, though, you need to be able to steer the front end, because there's no way you're going to be able to bend that in a controllable fashion from the surface when this thing is kilometers deep. So there's active steering at the front end. And here's how it works. This is what's called a drill collar. The sort of ugly drill bit gets screwed onto this end. I actually have another picture that I should have used, but showing the drill bit, 8-inch drill bit on this end. And it's in the chapter, good. So yes, good. I did use it there. And then this end is connected to these kilometers of steel pipe that go to the surface, where it's rotated on this rig that you've seen in movies and so on. The main purpose of that rig that stands on the surface of the earth is basically to turn 4-inch drill pipe. That's all it does. And so the way you steer is by these clever little pads. You see 2 of them here. And here's a cross-sectional view. They're actuated by pistons. And so here's how it works. Let's say that I want to drill out the door, and I'm standing here. So as the collar rotates, the pad that's on this side gets pushed out by the little piston, and that sort of urges the drill bit to go in that direction. As the drill bit makes another third of a turn, then the next pad is going to press up against me and tend to push the drill bit out, and then another third of a turn this one. So you'd sort of gently urge the drill bit to go in a particular direction, pushing it toward the direction that you want to go. And I think you can easily see that not only can you steer this thing in any direction, but you can actually even make it go up or down, and that's quite common. So so that's sort of the trick for steering. There's also other methods of steering bits, but that's kind of conceptually the simplest one and also becoming increasingly popular. Now, how well do these work? So here is an actual trajectory for drilling. On the horizontal axis is distance sort of on map view, kind of looking down from 8,000, so this is 8,000 to 16,000 feet, so that's an 8,000-foot run. Here's the depth in feet, and you'll notice that each division here is 1,000 feet on the horizontal axis, but it's only 25 feet on the vertical axis, so there's considerable vertical magnification, yes.
How does the drill bit actually position itself underground?
Just what I said. So basically, it's going to be going down vertically, and then until it gets kicked off.
Right, but how do you actually know where the drill bit is positioned underground to tell us this is where you need to turn and this is...
Right, okay. So that's a great question. There's all kinds of instrumentation in this collar. Things like compasses, gyroscopes, tilt meters, and so on. And the information gets sent back to the surface in a very interesting way on mud pulses. And so the drill knows exactly where it is, but with this basically navigation, inertial navigation instruments. And then the information gets sent back to the surface, so the driller has a display, a map display.
So if it's using gyro and accelerometers, it can drift over time, though, unless you have another system.
Yeah. Actually, the precision is pretty darn good, and in fact, I'm going to show you in a minute an example of that. Precision's pretty darn good, but if you really want to be careful, you can also do what's called a directional survey, which is after you take the drill bit out and all the drill pipe, you can lower in a tool on cable that has even better instruments that do not have to survive all the vibration associated with drilling and get very accurate trajectories. Yeah, so there's a double check if you need it. But just to show you how good this system is, this is a drill trajectory, and the objective was to stay between cyan and magenta layers, whatever they were. This was not one of our jobs. It was sort of brand X. And so here they are, sort of chugging along, following that interval. And there's also methods of measuring where you are with respect to bed boundaries, both mostly electrical. And here you can see that it encountered a fault that's about a 20-foot throw. And so, oops, now we're no longer following the boundary between magenta and cyan. It takes about 1,000 feet to recover that 20-foot discontinuity, and now once again he's traveling along the desired path. So I would say pretty good for brand X. It wasn't a Schlumberger job, but they did well. Okay, so once you have the ability to drill from anywhere to anywhere, this gives you an enormous amount of freedom to intelligently develop oil fields. So this is an example. It's from the Barnett Shale. So somebody decided they wanted to produce gas from underneath the University of Texas at Arlington, and it would be disruptive to the students to have drilling rigs all over the place, obviously. So they have one little 5-acre site down here in the southeastern corner of the campus, from which they developed about 2 square miles of gas reservoir. And by drilling down, and then, as I explained, steering the drill bit in various directions. And so here the entire campus, it looks like most of the campus is sort of under production. This looks kind of like a light industrial area, and then even here under this kind of nice looking, probably residential area. Of course, at this point the well is like several kilometers deep, so the people here don't even know that it's beneath them. Yeah.
Oh, so I can understand sort of how the horizontal well works in one dimension, but that like the top one seems to have made like a left right angle. At least I
You mean, what you mean like this?
yeah, like that one. So that kind of seems a little off because as we'd be drilling in one direction, and then you turn it again, wouldn't that create a lot more, I guess, difficulty in the horizontal drilling because now you're not only going.
Yeah, that's a good question, and whether these are actual trajectories at the same level of accuracy as the previous slide, that one, I can't really guarantee. It might have just been sort of a, let's take a magic marker and sort of follow the approximate trajectory sort of display. It kind of looks like that because these look a little bit too uniform. But keep in mind that it's going down and turning in 2 axes at the same time. So it can be a relatively smooth curve. And of course, we're only looking from the top down. Yeah. But I'd need to look to see whether this obeys the 10 degree per 100 foot limit. That's the question. And I haven't done that, but I will do it. Well, in fact, because if it is going down like this, it would be easy to show this on a projection. Yeah, it would look like this on a projection, even if the curve is much less severe. Yeah, that's a good point. Okay, yes.
So I understand how it steers, but then how do you actually propel the whole thing forward? Like, does the collar have some threads on it or something?
Yeah, the drill pipe is heavy. So, it's steel pipe, and you put it down, and it sort of gets, and so there's a lot of what's called weight on bit. So all the drill pipe above is applying pressure to.
Through all these curves, like
Yeah, yeah. At 10 degrees per 100 feet, yeah, it's adequate. Yeah, yeah, that is adequate.
I guess to add on to that, one of the questions I would have is when you start going back up, how do you actually exert force from the rock?
That is a good question. Weight on bit when you're drilling up. I think that you do have like thousands of feet of sort of vertical drill pipe coming down, and so even if you're going up a bit, I think that doesn't nullify that. It's kind of like a hydrostatic problem. I'd like to think that through a little bit more. I think that's a decent question, but I think the answer is going to be that basically you've got enough weight from the vertical section that it's adequate even to propel you up. Yeah.
Are the green dots with no lines are the wells?
The green dots are basically the end of each well.
Right, there's like 4.
Yeah, I saw that. Like this little, what's this green dot doing here? Honestly, I don't know what that green dot is. To tell you the truth, I noticed it too, and I thought, what is that green dot? But I did not use magic marker or something to blot it out because, for the sake of honesty. But honestly, I don't know what it is.
Cool house painted in green.
Possibly. Yeah.
So 2 miles means we can drill from Harvard and suck all the oil from MIT.
Absolutely.
So which means there's some legal issues here. So how to solve that?
Oh, yeah, okay, yeah. Okay, so that is a significant problem. And in fact, at the law school, there's a course that's all about oil and gas law, and a lot of it is, where the heck are you drilling? And I was asked the same question. I was asked the same question there. Let me just get rid of this. There are state laws that provide how to divide up the revenue from the well according to who owns the property above the well. And so when I mentioned this directional survey where you send down the instrument to find exactly where the well goes, the lawyers are keenly interested in that. Where does that well go? Is it underneath my client's property? So yeah, so this is a big deal. Yeah. Yes?
Sorry, I have no questions, but
Yeah.
is horizontal drilling used for anything but oil and gas extraction, like sewers or water distribution or power underground?
Right. So yeah, there's this sort of the civil engineers use what they call a mole, which is kind of a similar. I'm not exactly sure of the exact technology, and it's not exactly the same because you don't have so much weight on bit from the vertical drill pipe because you're only drilling down tens of meters maybe. But there are moles that will tunnel underneath a street, yes, without digging it up.
Is that used often compared to traditional trenchless street?
You'll have to talk to your civil engineer friends about that. But it is used, and they're not uncommon. Yeah, and like if you want to drill underneath a stream or something, that's very common. Where trenching is not not possible. Yeah. Okay. Okay. So how do you fracture the well? Now, it may seem like the oil and gas industry does fracturing, just to annoy environmentalists, but that's actually not true. It actually is an essential part of developing this resource. So let me give you some. I'm going to sort of explain how to do it, and I'll give you some numbers that you can sort of hang your hat on. So, typical well is about 2,000 meters of horizontal run. To do all that fracturing that I mentioned takes about 20,000 cubic meters of water, these days, more than 4,000 metric tons of sand, and about 200 metric tons of chemicals. Now, the industry is really fond of saying that, the chemicals are only 1% of frac fluid, and that's true, but 1% of 20,000 cubic meters is 200 metric tons. That's a lot of trucks on the road going out to the well site full of chemicals. So don't be fooled by the 1% number. Now, once you mix up that witch's brew, which I will talk about in a few minutes, it's pumped underground at a rate of 25 cubic meters a second at a pressure of 70 megapascals, which is 10,000 psi. That's a very high rate of high pressure pumping. To do that, you need lots and lots of trucks, as shown here, typical Schlumberger job. Each truck generates about 2,000 horsepower of pumping capacity. You require about 24,000 horsepower. You're looking at more than 24,000 horsepower here because some of the trucks are spares and they're not run at full capacity. But basically, they put high pressure frac fluid into a manifold, which is sort of this thing, which goes into the well shown down here. So it is a big industrial operation. And because you have multiple wells at each 5-acre site, as shown in the previous slide, these guys are basically on station for a month at a time. So there's going to be, for the neighbors living on the other side of those trees, there's going to be a lot of disturbance it's going to be a month of hell, let's face it, with all these trucks running and it's noisy, and trucks coming with water and sand and chemicals. It's not a pretty picture. In a month, it's all over, and you just have basically a pipe coming out of the ground. But this is a problem for people who live in these areas. Now, you might also ask, 20,000 cubic meters, how much water really is that, 20,000 cubic meters? Well, an Olympic-sized swimming pool, so 20,000 cubic meters is about 5 million gallons. An Olympic swimming pool is about 1 million gallons, so you need 5 Olympic swimming pools worth of water to fracture each well. And you might have 6 or 8 wells on a site. So you're going to be bringing in 30 water equivalent to 30 Olympic-sized swimming pools in trucks, or slightly better technique, in a pipe onto that site in a month. Yes.
So is a gas pipeline made towards this well by the time it's done being fracked? and
Yeah.
produced? Why isn't that pipeline used for water before the gas is produced?
Different specifications and also different destination. So where you do have local water available, and I have seen this in Pennsylvania, you'll take water out of the nearby river. It'll come up in PVC pipe, 1-foot pipe. Gas pipe is really different. It tends to be buried, for one thing, because it's going to be permanent. It's steel pipe, and it's not going back to the river. It's going to the gathering system. So it's a totally different pipeline system.
So shale gas production is really water intensive, right?
We'll talk about how water intensive it is on the next slide. Yes?
Once you set up the wells, it sounds like it's like about a month's startup time to go in, do all the drills you want.
A couple of months, including the drilling.
Does
Yeah.
that include time for, I'm assuming that Schlumberger also has like methods for capturing like fugitive emissions or controlling
Mhm.
weight. So how does that work in terms of like installing it? Like what are some strategic locations?
Yeah.
'Cause, I mean, I guess you can't just assume that there's only fugitive coming out of the pipe that main well, right? There's like probably stuff in that area.
Well, that is a great question, and in fact, one of my personal projects is methane emissions from well sites. I was just talking to the Environmental Defense Fund on Wednesday. We had a 4-hour meeting on that subject. And so we're developing a sensor system in which they would like to test. There's lots of ways that methane can escape, and just for background, methane is a greenhouse gas roughly, depending on how you look at it, 25 to 100 times more potent than carbon dioxide. So it is really an important greenhouse gas, the significance of which I think has not been sufficiently appreciated in view of the many places it can leak. Well site is one of them. So the EPA has developed what's called a green completion, which is a way of minimizing methane emissions from well site operations. And those, when they're used, those can be very effective. I mean, they cut down emissions by more than 90%. This is what the EDF people told us. So that's a good thing. Right now, and back in the middle of the year, the EPA specified some rules about finding and mitigating leaks at well sites and distribution centers and processing plants and so on, which are still in place as of today. The fate of those rules is very much in question because the administration has promised to get rid of them. They have gotten rid of them on public land already, BLM rules. But the EPA rules are still in place, at least for the time being. So this is a matter of, I think, considerable concern if you're interested in greenhouse gas emissions. Considerable concern. So let's get back to water. So somebody said, wow, that's a lot of water. Yes. So the 5 million gallons I was talking about is 15 acre feet, and to a farmer, 15 acre feet is not all that impressive. So let's take a concrete example. I worked this out at the request of the California Council for Science and Technology. They were doing a study on hydraulic fracturing in California. So I said, okay, let's take the total number of wells that are hydraulically fractured in the United States in 2014, which was the peak year. It was 15,000 wells, each of them consuming 15 acre feet of water, 225,000 acre feet per year. That's the water we're talking about. That's all those swimming pools. Now compare that to agriculture in California. If you look at all crops in California, 34 million acre feet per year. This is nationally, this is just California. 34 million acre feet per year. And if you just look at the alfalfa that's grown in California, it's 5 million acre feet per year. Now, I'm a native Californian. I know what happens to that alfalfa. It goes for dairy cows. So basically, we're spending 5 million acre feet a year in California to raise dairy cows instead of raising them in Vermont, where it would need to be irrigated. So decide for yourself the significance of this number. So looking at a national level, I mean, water use can provide problems at local levels for, limited periods of time, but on a national scale or even state scale, it's really not significant. Okay, I've got 7 minutes left. We'll talk about fracture fluids. Yes?
Sorry, just a quick question. Does horizontal drilling necessarily, sorry, do you necessarily need fracturing when you use horizontal drilling? Like say there's an oil well that is underneath some, hard rock that you wouldn't want to access by vertical drilling.
Yeah.
In that case, you wouldn't necessarily want hydraulic fracturing as you're moving towards the
Yeah.
oil well, right?
Yeah.
So is there a way to sort of avoid hydraulic fracturing while you're doing horizontal drilling so that you can get that without the
Yeah, and it's funny, if you look in the petroleum literature, for a long time people thought, well, we can do horizontal wells and we can do hydraulic fracturing. Why would you want to do both? It was like kind of one or the other mentality. And many horizontal wells have been drilled without fracturing, many. But in order to develop the 200,000 or 500,000 square meters, you've got to have both. That's where you need it. You need it for the surface area in these very, very low permeability rock. Okay, fracture fluid requirements. So fracture fluid is another one of those topics that has been very much debated. Okay, Mike, so I can either talk about fracture fluids or I can talk about rest of world. What do you think?
Who wants to hear about fracture fluids? Who wants to hear about rest of the world?
Okay. I think the fracture fluid people won. That's a bunch of techies. Okay, fracture fluids. And if you want to hear about rest of world, I am available afterwards, and also we can do some little supplemental topic, and you will have all the slides. Okay, so this will have to be quick, though. Fracture fluids have many requirements, and they're listed here on this slide. They have a lot of functions. You have to prevent corrosion. You have to make sure nothing gets deposited in the well. So there's lots and lots of stuff. You will get this slide. The two biggest ones are the two that I've noted with the blue arrows. One is that it must be pumpable at high rate without excessive pressure drop. And the second, that you have to keep the proppant in suspension. Okay, proppant is all that sand, the thousands of tons of sand. Basically what happens is when you create the fracture, it opens. But if you take the trucks away, the fractures will close up and therefore not give you a flow path. To keep the fractures open, you need to fill them with sand, which is highly permeable to fluid flow, and that keeps the fracture open. So you have to carry sand down deeply into those fractures. And so how do you do that with water? Well, anybody who's been to the beach, here's a frac fluid designer sort of in the future. Anybody that's been to the beach and had a bucket of water and dumped a shovelful of sand knows the sand goes straight to the bottom. Winding up at the bottom of the well, doing you no good. You have to carry that sand into the fracture. So you need something viscous to keep the sand in suspension, I guess, but not viscous because you need to pump this stuff at 10,000 psi, a quarter cubic meter a second. What do? Well, there are friction reducers. Here's two examples, polyacrylamide, guar, fascinating, really, really fascinating chemistry, which I'm not going to cover in the next 3 minutes, so let's move on. But this is an example of these special fluids. They're called shear thinning or non-Newtonian. Basically, the property is that at low shear rate, down here, they have high viscosity. So if you just sit quiescently, it looks like a very viscous fluid. When you force it to flow fast, you have high shear, and the viscosity goes down. So these are nonlinear fluids with very peculiar properties. And, okay, why is this useful? So one thing is, at high shear, these molecules, which are sort of long polymeric chains, at low shear, they're sort of like tangled up and very viscous. At high shear, they stretch out, and the viscosity goes way down. It's these two. Also, a shear thinning fluid has the property that its shear is very low at the center of the pipe and high at the boundary, higher than in a Newtonian case. So any sand that finds itself here is in a low shear regime. In other words, the fluid is very viscous in the middle. And however, at the wall, the shear is high and the viscosity is very low, so this stuff supports sand in the middle of the pipe and slides easily through the pipe at the edge. And moreover, with this kind of fluid, the particles are pushed to the center where they are most supported. So this is like really magical. And I think I will finish with this slide. This is a cross-linked gel, Schlumberger's finest. And basically you can see this is kind of like gloppy and it will suspend sand, no problem. But if you take that beaker and tip it a little bit more, this stuff just plops out. It just bloop, falls out. And that's because you're developing a lot of shear at the beaker wall, and the viscosity gets very, very small and slides out easily. So you can have a very viscous material holding sand that slides out very easily through a pipe. What? I should have brought some along, actually, yeah. Anyway, it is 4 o'clock. It's 3:59. So I will stop here. I have more about rest of world. I have more about flow through porous media. Please come and see me if you'd like more details on either, and you will get all the slides in a packet.
Follows